Okay, we're going to talk about planes that are tangent to surfaces. So pretend you got a surface and point, and our goal is to find the plane that is perfectly tangent to that surface at that point. Let's assume that the point has coordinates A, B. Now, this is something interesting. We're assuming that this is a function f of x, y. And so C, which would be our third coordinate, is really the same thing as f of AB. So sometimes we will only give AB, and sometimes we'll give you ABC. It depends. If we only give you AB, then it is your job to find C. And if you're given ABC, it is also your job to make sure that that C value actually matches the function. Anyway, so we have the point there, and we want to find the equation of this tangent plane. If you have a generic point x, y, z on the plane, x, y, z, then this vector um, will have coordinates. Again, this is A, B, and C. A, B, C. This vector will be x minus A, if we subtract, y minus B, z minus C. And if we figure out the normal vector, let's label it as little n for normal vector, the dot product should be equal to 0. And that will give us the equation of a tangent plane. I'm going to develop how to figure this out, and then I'm going to show you a shortcut to find the actual tangent plane to a surface at a given point A, B, C. So the key now is to figure out what this normal vector is. Okay, I'm going to draw a quick picture again. So there is the tangent plane, and the tangent plane will share the slope in the x direction and the slope in the y direction, yeah, as the surface. Because they're tangent, they're going to be almost the same at that point. The tangent plane and the surface are going to be very, very much the same. That's the whole point of tangency, that they're going to be, one is rigid, one is straight, rather. The other one is curvy, perhaps. But they're going to be almost the same at this point of intersection, at this point of tangency. So the slopes are going to be the same. And the slope in the x direction is going to be the derivative, the partial derivative with respect to x, and the slope in the y direction is going to be the partial derivative with respect to y. Now remember what slope means. Slope means rise over run. So slope means rise over run. So if you have a slope of 2, what does that mean? It means 2 over 1, which means 2 up for 1 across. So this is a slope of 2. This is physically what we mean by a slope of 2. 1 over and 2 up. So whatever the slope is, if you think of it as that number vertical and 1 horizontally, you will end up with that slope. Okay, so if this is the partial derivative, this vector represents the partial derivative in the x direction, then this vector on the plane will have coordinates. Okay, so we are in the x direction 1, no y motion, no, not going left or right, and then 1 unit towards us, and then f sub x up or down. So this vector on the plane will have those coordinates. This vector on the plane will have coordinates 0, 1. So it's going to go on the right. So that is 1, just like here, 1. And then f sub y up or down. Yep. So we can represent those two vectors with 1 of f sub x, partial of f with respect to x, or 1 partial of f with respect to y. If we cross those two vectors, we get this minus that negative f sub x, comma, that minus that, but then do negative, negative f sub y, and then 1. So the cross product of those two vectors is this, and that is precisely a normal vector. It is going to be perpendicular to those two. So this n can be represented by this vector. It is a normal vector. And so if we multiply, I'm going to put n first. N dotted with x minus a, comma, y minus b, comma, z minus c. We want that to be 0, but that is equal to negative f sub x, comma, negative f sub y, comma, 1. And that is equal to negative f sub x quantity x minus a minus f sub y quantity y minus b, and then plus 1 times z minus c. And because we want those two vectors to be, no, this generic vector and this normal vector to be perpendicular, we want the dot product, this dot product to be equal to 0. So if we solve this equation for z, and we move everything to the other side of the equation, so z would be, this term goes to the right as positive, f sub x, x minus a. So that's this one, f sub y, y minus b. Z stays where it is on the left side of the equation, and c moves to the right, plus c. So this is the way to obtain the equation of the tangent plane. Find the partial with respect to x, find the partial with respect to y, multiply by x minus a, x minus b, respectively, add c, and voila. Let me rewrite this again here. Z equals f sub x, x minus a, plus f sub y, y minus b, plus c. I'm going to change this a little bit. I'm going to rewrite it as m sub x slope on the x direction plus m sub y slope in the y direction. You don't have to underline it. I'm emphasizing that it's a slope, y minus b plus c. The reason why I like this equation a little better is because I have found over the years that students do not plug in the number a and b to figure out the partial derivative. They simply leave it as variables, which does not give you a plane at all whatsoever. So remember, these are fixed numbers. Fixed numbers. Numbers. Let's start with an example. Example 1. Let's say you have z equals, which is the same thing as f of x, y. Sometimes I'll write it as z, sometimes f of x, y, same thing, but x squared plus y squared. So we got a nice paraboloid, very, very symmetric paraboloid. There's the y-axis, the x-axis, and let's focus on a point 3, 4. So 1, 2, 3, and then 4. So that's the input, 3, 4, which corresponds to an output up here on the surface, which is going to be 3, 4, 25, because f of 3, 4 will be 3 squared plus 4 squared, which is equal to 9 plus 16 equals 25. And we're not going to take the square root of that, even though it is tempting, because the square root of 25 is so nice. But we're not going to do that. This is way up here. And we want to find the plane that is perfectly tangent here. So it's going to be touching the surface right at that one point. This surface curves up and down and curves around. So when we approach plane, at that point, we're going to be touching it only once. That is not necessarily always the case, but in this case it is. So we want to find the tangent plane. This is cool because there's no up or down or left or right. It's when we did calculus 1, we were talking about the tangent to a curve at a point, and but typically we always thought of the tangent this way, but now we're thinking of the plane going all different kinds of directions. Anyway, so this point up here is 3, 4, 25, and we want to find the tangent. We're going to use this formula up here. So go back to f, find the derivative with respect to x, which is 2x. Find the derivative with respect to y, which is 2y. That was symmetric. And here's where I'm making the distinction between f sub x and m sub x. This is the slope we're actually going to use at that point. So I'm going to plug in 3, 4 here. So the slope at this point will be 6. Because we're plugging 3, 4. This expression does not use 4. It only uses the 3. Still, we're plugging in 3, 4. M sub y will be 8. This expression does not use 3. It only uses the 4, the y value. But still, I'm going to speak in terms of plugging in 3, 4. So we're plugging 3, 4 into this formula, even though this formula only uses y, only uses 4. And we're 2 steps from getting the final answer. So z equals 6 times x minus 3, according to this formula, x minus a. So this is a, this is b, and c would be this guy. Plus 8, this other number, y minus 4, plus 25. That's the answer, except we prefer to consolidate all the constants. So z equals 6x minus 18. 6 times 3 is 18, plus 8y minus 32 plus 25. So that is 6x plus 8y minus 50, because negative 18 minus 32 is negative 50. We added 25. That's a coincidence that we end up with negative 25. So z is equal to 6x plus 8y minus 25. And there is the equation of this plane that is tangent to the surface at that one point. I think this is very, very neat. That's the way we find the tangent plane to a surface at any given point. Yeah. Let's do one second example. I was ready to finish here, but let's do a second example. Example 2. I just thought of one that may be of interest. So f of x y equals, let's say, 1 over the square root of x squared plus y squared. Yeah, so this is going to be always positive. The farther away x and y is from the origin, the more this will be, because this is actually the magnitude of the point. And so we end up with this kind of surface. It has a huge asymptote here. And there. It's a circular, sort of a hyperboloid. Yeah. And this extends forever and ever and ever and ever through the whole plane. So pretend that's that. And the asymptote happens at the z-axis. So there's no point at 0, 0. Let's take a nice, easy point here. Let's make it symmetric. So 1, 1, if x is 1 and y is 1, so let's say this point is 1, 1, and that's going to go up to the surface. So we plug in 1, f of 1, 1 is going to be 1 over the square root of 1 squared plus 1 squared, which is going to be 1 over square root of 2. So the point up here is going to be 1 square root of 2 on the surface. 1 square root of 2. And we want to find the plane that is tangent to the surface at that one point. So that plane is going to be sort of inside. Eventually it's going to come out, but it's going to start out because this is curving this way. The plane is initially going to be inside, but then it's going to come off outside of this. It's not a cone, some kind of horn. I'm going to call it a horn. All right, so we want to find that plane that is tangent to the surface at that point. Well, the formula calls for z equals m sub x, x minus 1, remember the x value, plus m sub y, y minus 1, plus c. And we know c is the square root of 2. We just found that out. Actually, well, it is 1 over the square root of 2, not just square root of 2, because we're in the reciprocal. Okay, so the only thing left to do is to figure out the m sub x and m sub y. Let's see. The derivative of the function with respect to x. Okay, so we're doing derivative with respect to the square root. And all of us know that we have a denominator of 2 times the same square root. That's just from calculus 1, doing many, many derivatives with the square root. And then on the numerator, we're going to, using the chain rule, we're going to find the derivative. We're going to write down the derivative of x squared plus y squared. Now we're doing the partial with respect to x. So that means 2x, because y is going to be constant. Again, the reason why we have 2, well, let me back up a little bit. I'm using the power formula. So this is a side note. Yeah, if you have x to the negative 1/2, and you're using the power formula to find its derivative, this is from Calc 1. That is going to be this is in the denominator, so good thing I'm checking. Negative 1 over 2. I'm not having enough room here to write it, so let's do it again. Negative 1/2 derivative, because that's what we have is a denominator. So the derivative is going to be negative 1/2 x to the negative 3/2. Putting this in the denominator, or with a positive exponent, we end up with 1 over, well, there's a negative, 2 times x to the 3/2. Ooh, good thing we checked. So there's an extra negative we should have here. 2, that's this 2, x to the 3/2. So this is the input to the 1/2, but then we got to cube that. So this side note is relative to Calc 1. I'm just trying to show how to obtain the derivative of 1 over a root. So 1 over a root is negative fraction, where the denominator has a 2, the same root cubed because of that. But then by the chain rule, we have to multiply by the derivative of the radicand with respect to x, which in this case will be 2x. Good. I'm glad we did this because, or I'm glad I did that because I was, it wasn't going to work otherwise as good as it wasn't going to be accurate. The 2's cancel or simplify, and then we can plug in 1, 1. So m sub x is the same thing as that, plugging in 1, 1. So 1, there's the negative, over 1 squared plus 1 squared is 2. So we got 2 square root and then cubed to the 3/2. There we go. So 2 to the 3/2. Which, by the way, is the same thing as 2 root 2. This is 1.5, so 1, 2, and as an exponent of a half, another 2 with a root. All right, Now, this formula is totally symmetric with respect to x and y. So if we are using the same numbers 1 and 1, we're going to obtain the same value for m sub y, negative 1 over 2 square root of 2. So z, going back to the equation of the plane, will be negative 1 over 2 root 2 x minus 1 minus 1 over 2 root 2 y minus 1 plus c. But c, remember, is 1 over the square root of 2. Okay, so there's the equation of the plane where the sun is coming in this direction and it's putting a lot of light into this, or shadow. But anyway, let's finish this up. Z is equal to negative 1 over 2 square root of 2x minus 1 over 2 square root of 2y. We still have to multiply this negative 1 with that negative, so that is going to be plus 1 over 2 square root of 2 plus, same thing here, 1 over 2 square root of 2 plus 1 over square root of 2. So z is equal to negative 1 over 2 square root of 2x minus 1 over 2 square root of 2y plus, if we add those together, we end up with 1 over the square root of 2 because each one of those is half of 1 over the square root of 2. So again, this plus that is 2, because it is the same thing, over 2 square root of 2. So the 2 simplify and we end up with 1 over the square root of 2 plus another 1 over the square root of 2. So we end up with 2 over the square root of 2. But 2 over the square root of 2 simplifies as the square root of 2. Voila. That is the equation of the tangent plane to this horn at the point 1, 1, comma, 1 over the square root of 2. Yeah. I think it would look prettier if we multiply by 2 square root of 2 and move things around, but I'm not going to do that. I'm just going to leave it alone. So there's the equation of the plane. And with this, we finish this video.